Hi, everybody. Welcome to this lecture on hypothesis testing. We are going to expand on our previous lecture and do different types of hypothesis tests today involving the t-distribution. So if you remember what we've done so far, the purpose of a hypothesis test is to see if our sample data, which is in the form of X bar, or sometimes raw data is provided to you, but either way, we're going to calculate X bar, and we're going to see if our X bar produces strong enough evidence or strong enough p-value to reject the null hypothesis. The null hypothesis represents a current belief, that is the status quo.
Okay, let's try this again. The null hypothesis represents a current belief, that is the status quo regarding a population parameter. And in the problems that we are working on, we're going to make mu the population parameter. Other types of hypothesis tests do have different population parameters, but in this semester, we're going to stick to mu. We have studied in the past lecture, we studied hypothesis test problems that provide us with a population standard deviation, and that's symbolized by the Greek symbol here, sigma. When we see sigma provided to us in a hypothesis test problem, we're going to follow the approach that we used in the last lecture. But in today's problems, we are going to see a sample standard deviation instead of the population standard deviation. We will not be provided with a population standard deviation. So when that's the case, like what we saw with confidence intervals, when we don't have the population standard deviation and we have the sample standard deviation instead, we use the t-distribution, which we discovered was also a bell-shaped distribution, but slightly different, a little bit flatter than the normal distribution with heavier tails. Now, for our purposes, we only really need to understand that we're using a different function on our calculator. But if we were doing this by hand, there would be a completely different mathematical function that we use for the t-distribution versus the normal distribution. So the sample standard deviation. When we had confidence intervals, which provided a sample standard deviation instead of the population standard deviation, we used t-scores instead of z-scores, and we used the t-distribution instead of a normal distribution. Similarly, with hypothesis testing, when the problem doesn't provide us with a population standard deviation and gives us the sample standard deviation instead, we will use a t-distribution. Let's do our first full-length hypothesis test problem, the effect of compression bandages on wound healing time. A medical team is studying whether the use of compression bandages reduces wound healing time. So this is important. Reduces is important because it gives us a hint as to the direction of the alternative hypothesis. Normally, the population mean healing time for similar wounds without compression is mu equal 14 days. So we have our status quo here, mu equals 14 days. The team applies compression bandages to a sample of n equals 64 patients and finds the mean healing time. This is our X bar, our sample mean is 13.3 days with a sample standard deviation of 3 days. Does the sample results support the claim that compression bandages reduce wound healing time? And we're going to be using a significance level of 5%. So this is a hypothesis test, again, involving a claim about the population mean, like last class. But what's different this time is that instead of being provided with a population standard deviation, we are provided with a sample standard deviation. So key takeaways, but from reading the problem, You want to understand that the current established population mean is 14 days. And that will become the null hypothesis. In the null hypothesis, we assume that whatever we are testing, in this case, compression on wounds, whatever we are testing has no effect. So we are going to, in the null hypothesis, we're going to assume that 14 days is the time for healing of this kind of wound. In the alternative hypothesis, this is a counterclaim. This is where we state the direction, and here's where we state that the population mean is less than 14 days. And we get that is less than because, in the words of the problem, there was this belief that adding compression would reduce wound healing time. So that's why our counterclaim is less than 14 days. So let's write our null and alternative hypotheses. So that's the first step of our hypothesis test procedure. We write the null and alternative hypotheses. The null hypothesis is where we state what the status quo is, the population mean healing time for a wound with compression band is 14 days. So here we're assuming that even though we're using a compression band, the result is the same as if we were not using a compression band. It's still 14 days. In other words, the compression band does nothing. And we symbolize that with mu equals 14. The alternative hypothesis is the opposite, the counterclaim, and we're going to state here the population mean healing time for a wound, again with a compression band, and this time we state the counterclaim is less than 14 days, mu less than 14 days. So we have our status quo with the null hypothesis, and we have our counterclaim with the alternative hypothesis. Next, we identify which distribution we are using. Now, last class, every distribution that we used was the normal distribution. Eventually, when we calculate our p-value, that's the probability value, and we do that to determine how rare the sample result is. When we calculate our p-value, we need to know which distribution to use. If we use a normal distribution, we will get a p-value based on the normal distribution, and that would apply to the previous lecture, but not to this lecture. So knowing that the distribution here, because we do not have the population standard deviation, and the sample size here, what do we have for? We do have a sample size, I think. Let me double check. Our sample size is 64. Okay, our sample size is greater than 30, but really, if we don't have a population standard deviation, we absolutely cannot use the normal distribution regardless of the sample size. So we have the sample standard deviation instead of the population standard deviation. Therefore, we are using the t-distribution. So because the sample standard deviation is given, we use the t-distribution. Step 3. Let's make a picture of this distribution. Let's identify the location of the mean, which in a t-distribution, which is also bell-shaped, the mean is in the center. The level of significance, that is always going to be 1 or 5%. And in this problem, it was 5%. And that level of significance is going to refer to the shaded critical region. And then across the top, we are going to label the 2 possible conclusions. So first, our bell curve, which is the t-distribution in this case. In the center of that curve, we have the mean of the sampling distribution, which is the same as the mean of the population, which is assumed to be 14. Because we are working with a less than hypothesis test, this test will be on the left-hand side. Remember, HA was stated that mu is less than 14. And because the use of the less than here, we want to put our significance level on the left side. So the leftmost tail of this distribution is going to get shaded in with 5% of area because that is the significance level. And the rejection region, rejecting the null hypothesis means we have strong sample evidence to prove or rather disprove the null hypothesis and reject the null hypothesis. That occurs when our p-value is smaller than this area alpha. If the p-value is smaller, it looks like this, an area that fits inside of the significance region. And that would put our x bar in the rejection region. We would be able to reject the null hypothesis. Now, the other way that we could conclude this hypothesis test is by failing to reject the null hypothesis. And that's going to happen when our p-value is bigger than alpha. So imagine that scenario looks like this with a p-value that's bigger than 5%. That would put our x bar here, which is not as significant a reduction as it would be if it fell in the rejection region over here. So there's two ways that this hypothesis test can end: reject HO or fail to reject HO. In step 4, we are going to write the decision rule that enables us to reject the null hypothesis. So this is a guiding principle, the decision rule, on how we will eventually be able to reject the null hypothesis. So the rule for rejecting the null hypothesis is that the p-value we get must be smaller than or equal to alpha. So we're going to write that. We can reject the null hypothesis and accept the alternative. Those things go hand in hand. When you reject the null, you accept the alternative. At an alpha of 5%, if the p-value of the sample statistic is less than or equal to 0.05. So the p-value of the sample statistic. The sample statistic is x bar, and its p-value, when we get to that point in the test, will be the area that extends all the way down to negative infinity. That will be its p-value. We compare that p-value to 0.05, and if it is smaller, then we can reject the null hypothesis and accept the alternative. So let's go ahead and try to do that. Let's get our sample data into the calculator and identify the p-value. So the function on the calculator we're going to use is the t-test instead of the z-test. So hang tight. I'm going to open up the calculator. Okay, so here's our calculator. We're going to go to Stat, Tests. We're going to go over to the Test menu and to number 2, t-test. And because we were not provided with raw data, we're not going to highlight data at the top here. We're going to go over to Stats and hit Enter. When data is given to you in the form of a list of numbers, you would use the data menu. But because we were given our statistics, we're just going to hit stats. We're going to come down here and put our mu sub 0 as the mean of the sampling distribution, which is the same as the mean of the population. We're going to put x bar as 13.3. It was given to us. Our sample standard deviation is 3. And our sample size is 64. Our direction is going to be, in this class I had mentioned in the previous lecture that I'm not going to use bidirectional testing, which is symbolized here with a not equal to mu sub 0. We're going to either do less than mu sub 0 or greater than mu sub 0. So what you're asked here is basically, what is your null hypothesis? Are you testing that the mean is truly less than 14? Or are you testing that it is greater than 14? Well, in this problem, we're testing that compression reduces wound healing time. So the answer here, the alternative hypothesis is less than. So you hit enter on the less than mu sub 0. Go down to calculate and hit enter. Okay, we got a few lines of output. The most important thing for us is the p-value. The t-score is also provided, although we don't use t-scores, or I don't teach using t-scores to make a conclusion, but it can be used. We use the p-value when we compare it to alpha. So take note of this p-value. We're going to take 4 decimal places, 0.0333, and also take note it's repeating the sample mean and the sample standard deviation and sample size. So we're going to take that and make note of it in the slideshow as well. Okay, so our sample statistic has a symbol or is symbolized by X bar. Its value is 13.3 and its p-value is 0.03333. All of this is asked of you on the homework that you'll see for this lecture, as well as the next test, the final exam. So now we have our p-value. Let's apply that p-value to alpha and do a comparison and make a conclusion. So let's look at our picture that we started and note where our significance level is. It's that leftmost tail. And our p-value, comparing it to 0.05, our p-value is smaller than 0.05. So we have a smaller p-value, 0.0333 is smaller than 0.05. The area fits inside of the significance region, and X bar at this vertical line, this dividing line, is in the reject HO region. And therefore, that is our conclusion. We're going to reject the null hypothesis and accept the alternative. We have strong sample evidence to believe that. So let's write that out. Note that the p-value is smaller than 0.05, so the conclusion is reject HO and accept HA at alpha equals 5%. So let's take a look at 2 ways that a hypothesis test could be. It could either be a test on the left-hand side or a test on the right-hand side. I'm going to show you a general rule on coming to conclusions in hypothesis tests. When making a conclusion, no matter which side the test is on, either on the left side, like in this example, or the right side, like in this example, if the p-value is less than alpha, the conclusion is reject the null hypothesis and accept the alternative hypothesis. So you always want your p-value to be smaller in area than alpha. And it does not matter if the test is on the left or the right, you still want that p-value to be smaller than alpha. So if alpha is 0.05, it doesn't matter if it's up here with this test on the right or down here with this test on the left, you still want that p-value to be smaller than 0.05 in order to reject the null hypothesis. Okay, so back to this problem. Let's go and answer the final question. We've rejected the null hypothesis. What does that mean? Does the sample results support the claim that compression bandages reduce wound healing time? And the answer is yes. The sample data supports the claim that compression bandages reduce wound healing time from 14 days. 14 days, if you remember, was the status quo. And our conclusion, and that was the status quo, was what we stated in the null hypothesis. Mu is equal to 14. The final conclusion that we made was to reject this null hypothesis. So we have rejected that it's equal to 14, and we've accepted the alternative, that it is truly less than 14. So when we're asked if the sample result supports the claim that reduce that compression bandages reduce wound healing time? The answer is yes. We have accepted the alternative hypothesis. The bandages result in healing times that are significantly lower than not using the bandages. So that is a full-length hypothesis test using the t-distribution. It's very, very similar to using the normal distribution, except it's a different function on the calculator. And so we're using t-scores in the distribution instead of z-scores. Nonetheless, a p-value is what we are trying to finally arrive at, and that enables us to reject the null hypothesis if it's small enough. So let's do another problem. New rehabilitation program for recovery times. A hospital claims that the mean recovery time for patients undergoing standard rehabilitation after knee surgery is 10 weeks. Mu equals 10 weeks. However, some medical professionals are concerned that the rehabilitation program might inadvertently increase recovery times. A random sample of n equal 100 patients undergoing the new program has a mean recovery time of x bar equals 10.5 weeks with a standard deviation of 1.2 weeks. Does this sample result support the concern that the rehabilitation program increases recovery times? Use an alpha of 1%. Okay, so important takeaways from reading the scenario here is that you have a status quo that is currently believed to be true, and then you have a counterclaim. You can read in the words of the problem that there's some concern that the recovery time is actually increased with this new rehab program. So you have the null hypothesis, the status quo, and you have the alternative hypothesis, the counterclaim. The current established population mean is 10 weeks for the null hypothesis, and the counterclaim is that the population mean is more than 10 weeks. So let's write that out with words and symbols using our standard approach for writing these hypotheses. We're going to start with the words the population mean, and then follow that with whatever it is we're testing. The population mean recovery time for patients undergoing standard rehabilitation after knee surgery. So again, the words start with the population mean, follow that with the variable that's being tested. Recovery time for patients undergoing standard rehabilitation after knee surgery, and then follow that with an is, because we never state a direction in the null hypothesis, and then state your status quo. And that symbolically is mu equals 10. HA, again, we start in the same way, the population mean, followed by the variable that's being tested, the recovery time for patients undergoing standard rehabilitation after knee surgery. And then we're going to say is more than 10 weeks, the counterclaim, mu greater than 10. So we've got our two null and alternative hypotheses, which are going to stay like this throughout the test. And eventually, when we make our conclusion, we can use the wording of the null and alternative hypotheses to help us interpret our conclusion. Because what does it mean to reject the null hypothesis? And what does it mean to fail to reject the null hypothesis? Coming back to these words could be helpful in interpreting the final answer. So let's go to where we have to choose our distribution. Based on whether or not we have the sample standard deviation, we will use the t-distribution, and that is what we have today. So because the population standard deviation is not given, we're going to use the t-distribution. The picture, because this is about increasing recovery time, the tail, the significance tail that we're going to shade in is going to be on the right side of this t-distribution. So we make our bell-shaped t-distribution. In the center, we have our standard population mean, status quo, 10 weeks for recovery. And on the far right, we shade in 1% of the upper tail of this distribution, and that is the rejection region. And everything else is the fail to reject region. So our decision rule based on this picture tells us the same kind of decision rule as the previous problem. Even though this is a test on the right side, it's the same decision rule. You still want your p-value to be smaller than alpha in order to reject the null hypothesis. And that's because the p-value for a right-sided test extends to positive infinity. And we always want that to be smaller than the significance region. So let's write how we will reject the null hypothesis. Reject HO and accept HA at alpha equal 1% if the p-value of the sample statistic, which is X bar, is less than or equal to 0.01. So we'll go to the calculator, calculate our p-value, compare it to alpha, and then make our conclusion. So next, let's go to the calculator and figure out what the p-value is. This decision rule is a guiding principle that we're going to come back to when we need to make our conclusion, but it's only a rule. This is not the conclusion itself. This is just the rule. Okay, so we have stat test number 2, t-test. Again, we do have the stats this time again, so we're going to plug them right in. Mu is 10, or mu sub 0 is 10. That's the mean of the population. 10.5 is the mean of the sample. 1.2 is the sample standard deviation, and the sample size was given as 100. And even though that sample size looks much bigger than 30 than what we need, because we do not have the population standard deviation, you could see here, the SX is the only alternative for us is to use the t distribution. So use the greater than mu sub 0 because the alternative hypothesis is that mu is greater than 10. So we're going to choose greater than mu sub 0 and calculate. Oh, I remember that I like to show you what draw looks like, and I forgot to do that in the last problem, but let me do it here. It does give us a nice image. Oh, and the p-value is coming out almost invisible here, and the p is coming out at 0. Let's take a look at what that means. Let's go back to, let me put this, stat test, t-test again. Let me go back to, instead of draw, let me do calculate. So my p-value has an e negative 5 here, which means that it's in scientific notation. And if we move the decimal place 5 spots to the left and fill those holes with zeros, when we round it to 4 places, it is 0. So we do have a very, very small p-value here. Let's go back to the slideshow. Okay, so looking at this scientific notation and writing it out, 3.309 e negative 5 means we have to move the decimal place 5 places to the left. Okay, and I'll put it here. When we take that 3 point and we put it 1, 2, 3, 4, 5 places to the left and fill in those spots with zeros, we end up with 0.00003. But traditionally, we are rounding our p-value to 4 places, which makes this 3 go away because we're rounding down. And so it rounds to 0. Our p-value is that small. It's 0. a very, very, very significant p-value. Our symbol for the sample statistic is x bar, and its value is 10.5. Its p-value, that is the area from 10.5 to positive infinity, is 0. Okay, so now our conclusion. Well, going back to this picture, we needed our p-value to be smaller than 0.01. Not only is it smaller than 0.01, it's practically 0. So our conclusion is going to be to reject the null hypothesis. P-value is smaller than 0.01. The conclusion is reject HO and accept HA at alpha equals 1%. So we've rejected HO and accepted HA. While we can come to a conclusion, sometimes it's not always easy to understand what that conclusion means in the context of the problem. So go back to the null and alternative hypotheses. So going back here, our conclusion was to reject HO and accept HA. So we are rejecting HO and we are accepting HA, which means that we are accepting that the recovery time is more than 10 weeks. We have evidence to prove that it is significantly more than 10 weeks. So when asked the final question, that's very helpful. Does the sample result support the concern that the rehabilitation program increases recovery times? And you'll say yes. The concern that the rehabilitation program increases recovery times is supported by the data. The mean recovery time is significantly more than the 10 weeks claimed by the hospital. Okay. So going back to the null and alternative hypotheses is helpful when you have to answer this final question and interpret your findings. Last, let's look at a problem that provides us with raw data. New medications impact on blood pressure levels. A pharmaceutical company develops a new medication it claims will lower systolic blood pressure. The mean systolic blood pressure before treatment in a population is mu equals 140. After administering the medication to 16 randomly selected patients, their blood pressure readings are, and these are the 16 patients' blood pressure readings. Is there evidence that the medication reduces blood pressure? We're going to be using a significance level of 5%. So in this problem, notice that we are not provided with X bar directly, and we're not provided with a standard deviation directly. But what we do have is raw data. And the raw data for the sample can provide us with both these things. And we'll be putting them into a calculator. We'll be putting this data into a calculator list and using that as input into the t-test function on the calculator. So I'm going to go to the calculator now and put these numbers in. Okay, let me go to Stat, Edit, and I have data in here from a previous lecture. I'm going to clear it out and clear out L2 as well. And let's put in, there are 16 patients, 139, 138, 141, 140, 137, 139, 140, 141, 139, 140, 141, 140, 139, 138, 141, and 140. Okay, 16 data values. Eventually, when we use t-test on the calculator, we're going to reference this list. Okay, so let's write our null and alternative hypotheses. The population mean systolic blood pressure after using the new medication is 140. And let's go back to the words of the problem. It says that before treatment, the population mean is 140. And in a hypothesis test, when we're testing some kind of product, we assume that it does not work. So the null hypothesis is the assumption that the mean is still 140 even after we give the medication. So that's why we write mu equal 140 for our null hypothesis. The population mean systolic blood pressure after using the new medication is 140, mu equals 140. And then now our counterclaim, the population mean systolic blood pressure after using the new medication is less than 140, mu less than 140. So we always specify direction. And in the null, we always specify the status quo. Okay, now we have to determine which distribution we are using. It's pretty simple. We're going to either have the normal or the t-distribution with these kinds of tests, and you'll always pick the normal if you have the population standard deviation. You'll always pick the t-distribution if you don't have the population standard deviation. In this particular problem, we were not directly given either population or sample standard deviation, but we have the raw data for the sample, which means we can get the sample standard deviation. It's impossible for us to go back and get the population standard deviation without the entire data for the population. With the data for the sample, we can arrive at the sample standard deviation. So for that reason, we use the t-distribution. Okay, we don't have either population or sample, but we have the raw data, and from that we can calculate the sample standard deviation. Therefore, we are using the t-distribution. Okay, we're going to go to create our picture now. This was about lowering blood pressure. So lowering means we're going to look at blood pressures on the left side of the curve, which is like this. Okay, so our rejection region is on the left side. We're going to shade in the bottommost 5% for a 5% level of significance. We will reject anything that falls, any p-value that is smaller than 5%, and we will fail to reject any p-value that's bigger than 5%. 140 is in the center. Our decision rule is our guiding principle on how we will reject the null hypothesis, and we are going to reject the null hypothesis and accept the alternative at an alpha of 5% if the p-value of the sample statistic x bar is less than or equal to 0.05. We need that p-value to be inside the critical region. That would indicate a significant reduction in blood pressure. So let's see what happens. We put the data into our calculator already. In this slideshow, I'm also using L1. And once it's in the calculator, we can go to t-test and refer to this data. So let me open the calculator now. Okay, so this is our list. Let's press stat and go over to tests and number 2. And across the top, we will select data because the information is coming out of a list. And notice that the list shows up here and it defaults to L1 for me. If you need to change that, second and the list name can change that list. Mu sub 0 is where you're going to put the null hypothesis, that is mu equals 140. L1, and you can keep frequency as 1. The test is a test on the left-hand side, so we choose less than mu sub 0. That's the alternative hypothesis, that mu is less than 140, less than mu sub 0. And I can calculate it or draw it. I'm going to draw it this time. I do like the way that looks. Okay, that's helpful. And the p-value is very visible. It's not small. It's 0.0842. I will also use the calculate function and show you the same thing using down at the bottom, instead of draw, hit calculate, 0.0842. Okay, so our p-value is not small enough in this case. Let's go back to the slideshow. So let's take note of the sample statistic. Its symbol is X bar. Its value, oh yes, I forgot to mention this while we were looking at the calculator. When you have raw data and the X bar is not provided directly to you in the words of the problem, you're going to pull it out from the output of the t-test function. So you're going to pull out, in this case, 139. I rounded to 2 decimal places, 139.56. Because it wasn't given directly to us, we had it in the form of raw data. We are finding that sample mean. By running the t-test function, we can find it. The p-value, 0.0842. Okay, so it's, while 139.56 is lower than 140, it's not significantly lower. And that's why we say, eventually we're going to say, here's the picture. It's not significantly lower, so this X bar, 139.56, falls in the fail to reject HO region. And that's going to be the conclusion for this test. Make the conclusion. We're going to say the p-value is not smaller than 0.05. The conclusion is to fail to reject HO at alpha equal 5%. Remember to say fail to reject HO and not accept HO. We want to make sure that we adhere to that convention. So going back to the words of the problem, we have just failed to reject HO. Going back to our null and alternative hypotheses, if we have failed to reject HO, it means we're not rejecting it. And while we don't say we're accepting it, when answering our final question, we're going to stick with the status quo. We're going to state that the status quo remains. So we don't say we're going to reject the alternative. We just say we're failing to reject the null. So we're keeping with the status quo. So let's go back to here. Okay. Now, so answering the question, is there evidence at 5%, alpha equal 5%, that the medication reduces systolic blood pressure? And here we have to say no. The sample result does not provide evidence that the medication significantly reduces blood pressure. While the sample mean was smaller, it wasn't significantly smaller. The mean systolic blood pressure after treatment is not significantly less than the mean systolic blood pressure before treatment in the population, which was 140. Okay, so that concludes the lecture on t-tests. It's pretty similar to z-test with that one exception. If you make the wrong choice, a z-test versus a t-test, you may get like half of the points of a hypothesis test question correct, but you'll probably lose a lot of points when you answer the p-value incorrectly and perhaps make a conclusion incorrectly because the p-value is incorrect, and answer the final question incorrectly. So a lot of points you can still get, but you really want to make sure that you choose the right type of test, because otherwise lots of points could be left on the table and you can lose those. So if you have any questions, please let me know. I hope this was helpful, And I'll see you at the next lecture, which is the last lecture. Yay. Have a good week, everybody. See you soon.